enabled version of the compiler. You can see right as soon as I run that, a thing pops up and it's streaming all the data. Now, it took a little bit longer, but not tremendously longer, maybe like a 10, 15% performance penalty. And I'm adding a lot of zones. All right, so let's take a look at what the compiler has been doing. Actually, to make this picture make sense to you, let me sort of re-explain how the compiler works. Again, well, if you're using this feature, which this program is, then when the compiler starts up, you can have a sort of a meta-program thread that's a whole program of its own and builds the other program, right? So in the telemetry display here, this whole block of stuff is a thread. This whole block of stuff down here is another thread. This thread up here is just my meta program, right? So all this stuff that you see up over here on the left, these little icicles down here, are all the meta program building itself. And then once it's built, all this stuff is it building the real full program down here. Now, what does it do? Well, remember in the earlier demos how we had like a message loop that sort of goes and cranks along and you read the message and see what's happening? That's what's happening here. All of these are us reading and waiting on and responding to messages. I should say, to be a little clear, let me zoom into this for a little bit so this explanation will make sense. I'm just using the mouse wheel to zoom in. This is not an averaging or a summarizing kind of a profiler. A lot of the times when people talk about profiling their code, you'll have something that gives you the average or the total amount of time spent in a procedure or whatever. And those are not that useful. They're useful for some things. Like if you have a really egregious problem, you can see it there. But a lot of times problems are in behavior of specific things. Wow, most of the time when I call this function, it takes a small amount of time. But once in a while, it takes a lot of time, right? And in something like this, you can see that problem very easily. What this is just a time log of everything that the program does that I care about. So left is the beginning of time, and then as we go to the right, we go on in time, and then everything that happened gets logged. So things at the top are functions earlier in the stack. So do compilation cycle is a function that's very high in the stack, or low in the stack, depending on how you think. And that calls something called compiler pump, which calls perform loads, which calls load file, etc. Right? Now, the time it takes for this, and then everything on the very left here, this is like probably the process getting started by Windows, is this first 8 milliseconds or whatever, right? So now the metaprogram takes about 27, 28 milliseconds, right? And then we're starting to build the real program. Well, about 30 milliseconds. Here we're adding files and whatnot to the real program. The real program starts building at about 30 milliseconds into the timeline. Now, and this was a kind of a cold run. Like if I run it a couple times, we'll probably get some that are warmer. No, those are all about the same amount of time. Well, we got one and then one a little faster and then one a little slower. So we'll just keep looking at the one that we're looking at. It's always good to do that a few times, just to be sure that nothing really weird like Steam didn't decide to download something while you're in the middle of doing something. Okay, now I was talking before about, okay, so now remember, okay, here's the meta program. It starts the main program building. This main program is building on its own thread. What does it do? Well, it loads all the files for the main game, that 30,000 or most of the 30,000 lines worth of code, and builds it. All of that happens here in perform loads, right? So perform loads, I'm going to zoom in and sort of scroll over. Perform loads, well, I zoomed in too far. Perform loads starts calling load file, and I can see which file, and I can see which file takes how much time. So string builder takes not that much time. GL takes like 2 milliseconds, right? Now, if you go through here, you'll just see all the files in the project. Okay, a lot of them are fast, some of them are slower. Mixer is pretty big. Okay, so you can get the idea from there of what's happening. But the point to make here is all of these files, so almost the entire program. The part that's not done in this orange, by the end of this orange band, is like we generate a small amount of procedurally generated code that we then mix back in, right? That hasn't happened yet. But all of the program text that's actually in files happens here, and it goes through the lexer and through the parser and is done being parsed in 61 milliseconds. And actually, remember, this number is inflated because it's got all this timing in here, where if you zoom in here really far, I've got timing gates around all this stuff, and that takes time itself, right? So on my laptop, for example, not running with profiling, this is under 50 milliseconds, right? In under 1/20th of a second, we've lexed and parsed this entire program. And that's basically a linear operation, because you don't need to cross-reference anything with anything else. So this part will just scale linearly. So a program 10 times as big, right, if you have the profiling hooks on, will be under 600 milliseconds, or around 600 milliseconds, right? And without profiling, will be under a half a second. So sometimes people think, lexing and parsing are hard or whatever. They're not really hard, right? We did 30,000 lines in 60 milliseconds. It's not hard. Now, the other thing to know about this is the absolute maximum number of how fast we can be. So recall, all of this is happening in one thread, right? This is all serialized. However, parsing is almost completely embarrassingly parallel. This is not a language like C or C++, where we need to wait to know what some symbols mean in order to parse. Every single one of these orange blocks down here can be parsed independently, which means if you have a job system, you can farm these out to a bunch of jobs and parallelize things, right, to the extent of however many processors you have. Which is why I was saying it should be easy to get at least a 3 or 4 times multiple on these numbers that I'm showing. Probably you can get a lot more than that, but 3 to 4 times is a little bit of a pessimistic estimate that, like, oh, we're going to be waiting on other threads sometimes, or just have contention for resources somehow, right? But let me zoom in here a little more because it's fun, right? So if we're going to load a file like main, let's go into main, right? So for here, this lexer set input from file, this is the time it takes to actually load the file off the disk. It's an SSD, so it's not that long. It takes about 90 microseconds. This is maybe time that I didn't profile yet because it's pre-lexer. And then, the lexer starts feeding tokens to the parser, and each of these is a top-level statement. So I can see top-level statements, and I can map these. So first of all, I have the location in the source code where this happens, right? Like line 1053 of parser.cpp, but I can map those back to, or I can provide more information if I want, right? In the same way that I'm providing more information here, I'm in this zone load file of profiling, but I supplied the name of the file. I also, I have an ifdef in the compiler to actually tell me which top-level declaration each of these is. I have it turned off right now because, it slows things down a little bit more if you do that. But it's tremendously useful if you're looking at the thing and you're like, okay, most of these are small, but like, this one's pretty big. Which one is that? What file and line am I compiling here? You can easily add that in there. This is a very useful profiling tool, right? While we're parsing this particular top-level declaration, we're making atoms in the atom table. We're reserving memory in our dynamic array, right? That took 77 nanoseconds of 232 clocks, right? You can think down at the level of tens or hundreds of clocks, which is very, very, very useful. If you're a serious low-level programmer, this kind of thing is kind of indispensable, really. Someone's asking, oh, the formatting here is a little goofy right now. This thing that I'm using is just today a super hot build that they gave me where you can scale up the fonts, which I thought would be good just for streaming. Because it's the first day they've had this capability, sometimes fonts get a little mashed together, right? Because, it just hasn't been tweaked yet. So, oh, someone asked, what do the colors mean? Those colors are set by me. So I set colors by sort of what module roughly we're in. So gray is like system, and then green is, I forget exactly. Green is supposed to be like semantics, but maybe I set the color wrong for perform loads. Orange is lexing and parsing, right? Blue, or sorry, no, yeah, green is semantics. Blue is bytecode generation. So between all these green blocks, so here I'm figuring out what types a bunch of stuff is. Oh, and then I'm sending messages back, because remember we have this message loop where you tell the user program what types everything are. So I figure out the type, I send the message back to the user program, then I build the bytecode. So we're done. Let me reemphasize this for a second. Okay, so this is the almost 3 seconds that it took. How long did that run take? 2.0 something seconds. 2.29, right. So LLVM itself is 2.0 something, and then we run the linker after that, which takes an extra 0.3 seconds, right? So here we're running the linker. Here LLVM is chewing on what we gave it. Here we give LLVM all that stuff. Maybe this part could go faster, I'm not sure. But sort of this part, while we're using the LLVM backend, there isn't a lot of latitude, I don't think. There might be, though. Who knows? But I don't think it's an order of magnitude, is what I'm saying. But the part that is doing all the advanced features of the compiler, the part that really determines what the language is, right, and how well it works. And I don't mean to slight, so LLVM has lots of advanced features in terms of optimization. But when I say advanced features of the compiler, I mean like semantic features like the polymorphism, and the operator overloading and the metaprogramming, all that event loop stuff. Every demo that I've showed this whole time of every feature of the compiler is happening, and it's all happening in this first 260, 270 milliseconds, right? By the time we get here, we're completely done with this 300,000 line program, right? And all of this is happening on one thread, and all of it is parallelizable, right? So all of this will get chunked up into, many blocks that are running in parallel, and this amount of time should go way down. We'll try to get the LLVM time down, but we're not sure how much we can get that down. But we'll have an alternative backend that'll go really fast, and I'll talk about that at the end. Are there any questions about what we're looking at here? These pictures are just really cool, and they're great for understanding the program. Oh, bright purple is polymorphism. So, if you zoom out, you can see it doesn't really take that much time on the whole, but as I zoom in, you can see okay, here's some files that are making heavy use of polymorphic procedures. Unlike C++ templates, which take forever, these are very fast, right? Let me look for a particularly long one. Here's a kind of a long one. Let's zoom down there. So we polymorphed something. It took a lot of clocks. It took 170,000 clocks, but that was 57 microseconds, right? We generated a new version of a procedure. If I put some more debugging info in, I could tell exactly what procedure that is. I can also do some stuff, so I can get a more traditional profiler view. If I right-click on this and say Profile Zone over here, you'll see who takes how much time. And, like I said, LLVM is most of the time. Type inference takes 50 milliseconds out of this whole thing. Building bytecode takes 17 milliseconds. Polymorphism, all polymorphism in the whole program takes 15 milliseconds. Our low-level array thing takes 11 milliseconds, and that's because we add a lot of elements to arrays. Note that we added 126,000 things to arrays. So I'm going to try and see if I can get that down. Like the parser uses arrays in places where maybe we could get around it and stuff. What else is interesting? The sort of pipe of, during one of the demos or at some time, I talked about the pipe that things go through in the compiler, about the run pipe and the build pipe and the size pipe, and those are all here. So a lot of things go through these pipes, but they go through in big batches. It doesn't take too much time, a few milliseconds per pipe on the scale of the whole program. Here's overhead from telemetry, which is very small. Questions about what we're looking at. Bytecode builder is spelled wrong? What? Oh, there's a typo in bytecode builder. That's great. It's because I typed that by hand. You can, if you want, telemetry will look up the name of a thing for you, but that one's typed by hand, and I typoed it. Okay. Anyway, that's I think that's the main thing that I wanted to show, is that the compiler itself, the front end, okay, the front end runs really fast. It's done with profiling overhead. It's done with this particular program in 275 milliseconds, give or take. That is extremely parallelizable. But also, right, the thing that I was saying is, in the short to medium term, I would like a faster backend than either the C backend or the LLVM backend, which both take about the same amount of time. Now, again, that's kind of nutballs, right, that I can output. So let me show you the output of the C backend, right? Oh, I rebooted, so I don't have my Emacs up. Let me get Emacs. So when you compile using the C backend, why is my font so small? Emacs must be scaling to the display size when oh, sorry guys. Anyway, this will help the file look big, so it's going to be fine. Right, when you compile to C, it outputs a C program full of stuff, and it's just a ton of, here's the type info for the program, and there's that in an array, and eventually, well, there's some data structures, and eventually we get to real code. Let's go to like line 40,000. Now we've got some actual code, which I don't try indenting nicely or whatever. This is old style, or kind of old style C compatible, so I don't use really that much in the way of advanced features, so that it'll run on a wide variety of compilers. And I really I don't indent much or anything because I'm trying to optimize for output speed. However, I'm not optimizing that hard for output speed because we're doing all this with fprintf over and over, and it takes like 0.2 seconds to generate this file. This file is 210,000 lines long, right? So it is faster for Visual Studio for me to write out a 210,000 line text file, and then faster for Visual Studio to read that text file, do all this redundant parsing and lexing like the stuff I just did, but on 10 times as much stuff, or 8 times as much stuff, and then generate an output file than it is for LLVM's API to generate a file without doing any of that overhead. So again, we're not experts at using LLVM yet, so there may be things we can do that are faster, but we've sort of been trying. We've sort of been trying to make it fast. This is to say that neither of those routes is going to be particularly fast. Yeah, so this is 210,000 line C file that we just spit out, compile it, whatever, right? Okay. So like I'm saying, though, a much faster backend, in theory, would just take our bytecode instructions, convert them directly to x64 instructions, write out an executable with minimal fuss, and be done. And so that would take time, but I don't think it would take more time than building the bytecode in the first place. And as you can see, building the bytecode is not that much time on here. In fact, if I zoom into some of this stuff that looks blue, this is actually the blue of you're not zoomed in. Right, the bytecode blue is not taking up most of that time. So these little blue blocks in between the green blocks are building bytecode. It's very fast, right? The green blocks are all the advanced features. Generating x64 instructions should be even faster than this. So it should be a really tiny amount of time. Like it should take up this red maybe or something. I don't know. Anyway, this is all just to say the medium-term plan is to provide a new option for an x64 backend, which I've started on right now, that outputs x64 assembly directly. When we get that working, which hopefully won't be too hard because we're going to use a very limited subset of instructions, when we get that working, then I'll transition to writing an output object file directly so that we don't even go through the assembler, right? So by the time I'm writing binary x64 instructions into an output object file, that should go pretty fast. Now, the annoying thing about that is that won't have debugging information initially. And what's great about the LLVM backend is it's doing all this debugging info work for us. So we're then going to see how hard it is to try and put debugging information in and whatnot. But that is the plan for the medium term, is to get everything, like let's give ourselves some slack and say our front end should be done in 300 milliseconds, right? For whenever this is done. And then, you know, we still might rely on this linker for now. So let's say that takes another 300 milliseconds. So like, until we get rid of the linker, we'll be at 600 milliseconds or under, and still without parallelizing anything, right? And then by parallelizing, we should be able to cut that down drastically. And then by getting rid of the linker, we should be able to cut it down even more drastically. Rather than getting rid of the linker, it might be possible to sort of isolate the symbols that go out, or generate all position-independent code, or do some things to try to minimize the amount of work that the linker does, which will be another option that we pursue. I think that I've said everything I wanted to say. Yeah. Long term. So that's the medium term plan. Medium term plan: parallelize the front end, generate an x64 backend. Right. In the longer term, I don't know what's going to happen, because, so like I'm saying, LLVM is great. It does a lot of work for us. It generates good debug info. It generates good optimized code. However, if everything I'm saying is right and not a bunch of BS, and if we can compile a big program in a fraction of a second, or a medium-sized program in a fraction of a second, and a big program in single-digit seconds, right? Then to transition back and forth between something that fast and something that's an order of magnitude slower, or 1.5 orders of magnitude slower, is going to be uncomfortable. And we'll cross that bridge when we come to it, but we might not be able to use LLVM in the very long term as our final backend, depending on how fast we can get it to go. But yeah, I think until then, and when I say long term, I mean years from now, right? So for the next couple of years at least, our serious backend will be LLVM based. It's doing a lot of work for us. It's had a lot of good effort put into it, and I'm very happy that we're able to leverage that effort. But there are drawbacks, and I don't want to be blind to the drawbacks, and I want to try to take them into account in my planning here. So let's take questions. Does anybody have